Okay, so this problem is going to be a good review for us for the fundamental theorem of calculus and the second fundamental theorem of calculus. And so if you remember on your game day study sheet, I've got for you the first fundamental theorem of calculus and the second fundamental theorem of calculus. The first fundamental theorem of calculus just says if you integrate the derivative, you get the change in the original function. What we use this the most for, honestly, is if you think about integrating s prime of t dt. So integrating the derivative would give you the change in the original, so s of b minus s of a. And so this is velocity. So if you integrate velocity, you get the change in the original function, being the original of the derivative, still the same thing here. And this is displacement. Okay, and I do need you to remember that if you integrate the absolute value of velocity, then that's going to give you the distance traveled. Okay, the basic difference there being if you have an expression for velocity versus time, here let's say this is 5 and this is 5, these areas. So if you integrate from, if this is A and this is B, we know that area above the curve would give us, if we integrated from A to, let's just say, whatever this spot is, that would give you 5. If you integrate from this x value to B, that would give you negative 5 because the area is underneath. So if you integrate from A to B, this would cancel out and would give you 0. Okay, so the displacement would be 0 if this was my velocity function, because basically I went forward 5, backwards 5, I'm back to where I started with, a net movement of 0. But distance traveled, hey, I walked maybe 5 miles and 5 miles back. The absolute value basically just flips this part up for you so that you get credit for the travel, even though you went back to where you started, and you would get the 10. Okay, so that's what we mostly use the first fundamental theorem of calculus for. The second fundamental theorem of calculus, you guys actually figured out yourself. It was like your theorem. And so I made you suffer through. I gave you different functions, and I had you take the derivative of the integral. And what you found is it came back to the same function. Now notice that this is a constant here. So you're taking the derivative of the integral. Here, we were taking the integral of the derivative. So it's kind of the same idea. But the derivative of the integral, and so you get a plus c when you integrate this, but then when you take the derivative constant 0, so we worked on all that. The key, though, is this bottom number has to be a constant. And so instead of integrating and then taking the derivative, you can just substitute this upper bound into your function, and that's the answer. Well, that's true as long as that's a constant and that's x. But you basically have to use chain rule. So here, if you look at this one, we have a constant and we have x squared. You're taking the derivative of an integral. And all I'm doing here is substituting x squared in for the t, getting that answer, but then times the derivative of the upper bound. Okay, so the next problem that I'm going to demonstrate here uses a lot of that. It's a fair amount of marks and pretty easy. Okay, so let's take a look at what they're asking us here. It says, here's your function. Notice, constant, and we've got a variable here. It says, write down f prime of x. Okay, so they know that's not supposed to be much work. Okay, it's only one mark there for that. So I just want to kind of write my function. Makes me feel better. Okay, now they want me to take the derivative of that. So f prime of x would be the derivative of the integral. Okay, so perfect setup here for that the second fundamental theorem of calculus. So I have a constant, I have an x. The derivative and the integral are essentially undoing each other. I'm just going to substitute the x in for the t. Okay, and so then this f prime of x would just be equal to ln of 2 plus sine x. And this is the only thing you had to show out of all that, but that's one mark. Okay, and then it says, by differentiating f of x squared, obtain an expression for the derivative of the integral from 0 to x squared of 2 plus sine t dt with respect to x. Okay, so first of all, let's think of what f of x squared would be. Okay, so this is f of x right here. F of x squared would just be substituting in x squared for all your x's. So let's just do that. That would be 0 to x squared of ln 2 plus sine t dt. Okay, so it says by differentiating that, find an expression for the derivative of, well, that's the same thing I've got. Okay, so that is f of x squared. They want me to take the derivative of that. So the derivative of this, we have to do just slightly more thinking. Still derivative of the integral, substitute in the x squared, but then times the derivative of the upper bound. Okay, so this is going to equal just ln of 2 plus sine of x squared times the derivative of x squared, which is 2x. So what we found here was f prime of x squared. Okay. All right, and then the last part of this says hence. So I'm going to be able to take advantage of what I've already done. Obtain an expression for the derivative of this with respect to x. Well, this is a little disturbing because I have not a constant in the denominator. So I'm sure we can get around it because it says I can use what I've already done. That's always a good sign. Okay, and it wants the derivative of this. Okay, and what I'm going to do is break it up. Okay, so you can break this up in basically between x and a constant. You could say the constant is 0 if you want, but there's going to be a constant between x and x squared. So you could say from x to 0, and then let me just kind of let you see the rest of this here. And you could say from x to 0, and then from 0 to x squared, but you can't just put a constant. You're assuming there is some constant between these two values, and you're just splitting it up there. Okay, so from x to c, and then from c to x squared, just splitting it in the middle and adding up the two integrals. Now this one we're happy enough with because there's a constant on the bottom. Okay, this one we need the constant on the bottom. Well, we can just switch our bounds, just make that a negative, and this would then go from c to x. Okay, and now both of them are like what we already need. And you can take the derivative of each one separately, and we've already done both of these in the previous parts. The negative would be there, you'd be putting in the x, so ln of 2 plus sine x. And then this one you'd be putting in the x squared times the 2x. And do they care how we leave it? That is an expression. You can factor out the ln of, nope, you're good just like that. I'm just going to factor that out, but I see that here I've got x and here I've got x squared, so I definitely have two different things there. We're going to leave that guy alone, and we've got it.